Hello and welcome to another episode of Rustacean Station. I'm your host, Alan Wyma. Today I'm with Jonathan Pallant, who is in the Rust working group for embedded systems and also working for Ferris Systems doing their training, right? That's what we talked about before. Welcome, Jonathan. How are you?
Yeah, good. Great to be here. No, we're here at Rust Nation and just taking a moment out from the talks, and a lot going on today, but yeah, really glad to be here.
Yeah, how's the talks? Because I think I just attended one so far. I think you attended...
I've attended about 3 so far. I mean, I know some people who are here who avoid the talks and just hang around with the coffee and the refreshments and do all the chatting in the corridor. But yeah, I dipped into a great talk just now on binary translation. Yeah, subject I'm interested in. I always take studious notes on my iPad, scribbling away while I'm listening, because it helps me remember the talks when I come back later. But yeah, no, it's been good.
Yeah, usually when people, I don't know how to say this, most software developers tend to use pen and paper, at least I think, because it's like we already know how bad software can be.
Yeah, I am a pen and paper person, and one of the first things I did when I joined Ferris Systems working remotely was stock up my home office with HB pencils and pads of writing paper. But I'm also quite disorganized, and I ended up with a lot of paper and no immediate way to file it. We had some discussions, tried a bunch of things. I've ended up on Apple iPad and an original Apple Pencil, which is bad because it's really easy to snap it when you charge it because it hangs out the end of the iPad when it's charging. But generally, it's fast enough for me to handwrite with, and I can get all the notes on my computer later. And weirdly, I find that the Notes app has gone and translated my handwriting into sort of searchable text, which seems like voodoo magic to me, but it kind of works, and I can search through my notes and go back in history. So it works for me, and now my desk is, I mean, I'm not going to say uncluttered. It's cluttered with different things other than pens and paper.
Lots of PCB boards, I would think.
Yes, soldering iron, vacuum desoldering station, an Amiga that's in half working order. Lots of in-progress projects.
Yeah, I kind of want to talk a little bit about that part, right? Because I don't know a lot of people doing this, but I mean, obviously you're in the space more than me, so you would know more about this, but making your own PCB boards and doing all this kind of work, you said that you got this work funded from Rust Foundation, right?
That's right. I had this sort of ongoing urge to knit two things together. I have, I guess many people do when they reach their middle age, they look back on their childhood years with nostalgia. I was a child of the 80s. We had BBC Micros in the classroom. I had a Commodore 64 at home. And you look at a modern computer and you think, gosh, that's a lot of computer. I remember when computers were simpler, when they only had 64K of RAM. I mean, they were, let's be honest, objectively terrible. Like compared to today's computers, they were not good. And much of what you do today, you couldn't do back then. But you could do some things with them, and they had a certain charm, and there's a certain joy to be found in getting a game to run on a machine with only 64K of RAM. You know, you don't have the luxury of space and compute time, so as a human, you get to make artistic judgments on what needs to fit in the system and what doesn't. So I had this great interest in computers from my childhood. The sort of retro computing hobby has exploded over the last 5 years or so. There's now, dozens of YouTube channels and great blogs and things like that. So that's sort of one hobby. And then I got into Rust in about 2016. And as a sort of a former C programmer, I've done a lot of Pythons, Pascals, Perl, PHP. I've done lots in the past, mainly C. And Rust just fixed a lot of the problems I was having with programming. It gave me the space in my mind to think about the interesting challenges of the problem I was solving and not the tedious bits like making sure you don't double free memory. So it solved a bunch of stuff. So I like retro computers and I like Rust. And I was like, well, there are no retro computers you can really program in Rust. LLVM only really supports current architectures. I think there is some support for the Motorola 68000, but the older 8-bit machines, don't have great support. Why isn't there a modern PCB I can buy with modern components that I can go and get from the store, online store, obviously these days, but that I can program in Rust? There are microcontrollers. They only have buttons and LEDs. There's no keyboard. I can't give them instructions. They do the job they are given. And there are computers, but they're too complicated. So I wanted to make an open source computer that was fairly simple, easy enough for one person to understand. It's not very fast, doesn't have a lot of RAM. And that project kicked off 2017, 2018, when I was just getting into Rust. And that project was called the Monotron. And what that ended up being was a Texas Instruments microcontroller. We had 8-color video, sort of a crude text mode. We had sound, so I could get a little bit of wavetable synthesizer going, so it could make some beeps and boops, and I had keyboard support. And I gave a talk at Rust Belt Rust. I was talking at Rustfest Paris about that time, and I finished that project up. RustConf 2019 was like the sort of the finale for that piece of work. And I was playing Snake up on stage. I was delivering PowerPoint slides, but they weren't done in PowerPoint. They were drawn as ASCII art, and they were presented from the computer itself, which the organizers were brave enough to let me plug my little sort of ramshackle homemade PCB into their big cinema projection system. And that's a nice reveal at the end of the talk. I can spoil it now. It's been on YouTube for a number of years. But at the end of the talk, I finished the slides and I'm like, look, press exit. I'm at a command prompt. We've got a computer. Let's go play Snake. The problem with that project was it was something of a tech demo. It was a bunch of features bolted on one after the other without any of those professional considerations for software architecture or design or any real sense of what I wanted it to do, because I just sat down and typed whatever seemed like the fun thing to do today. And I got a lot of features in it. It was never going to be maintainable. It was never really expandable. It did what it did, and I felt it sort of reached an endpoint. And so I made that decision that programmers are often tempted to make, and one I think I would perhaps advise against. And that decision was to throw everything in the bin and start again and do it all properly this time. And that has taken 3 years. We've been through the pandemic, changed jobs a couple of times sort of in the last 4 years. And what we've ended up with, the project is called the Neutron. And the idea is there's a family of PCBs. You can be Neutron compatible, like an IBM PC. And there's an operating system. And as long as you write the drivers for your board, I call it a BIOS, like IBM did, you can run the operating system on top. And it just gives you a little shell. You can type in commands, load things from disk. So far, we've got a picture on the screen, and we've got keyboard support, and we can make the little PC speaker go beep. And that is a custom PCB, which the Rust Foundation paid for me to make 25 of these boards and give them away as kits. So we gave away kits to people. They could apply to join the beta program, and they got a PCB with all the fiddly bits soldered. So they got a PCB with all the little fiddly bits soldered, and all of the big chips and all the connectors they could fit themselves. So yeah, that's been really successful. We had some good feedback on that. I don't imagine it'll ever turn into a profitable enterprise, but it's been fun, and it's been an excuse to write more Rust.
So I guess I can ask, what came of that? I mean, it's just that you delivered the boards and then that was the end of that chapter?
Well, I encouraged I call them the beta program members. I encouraged them to join us in the Matrix chat. It's #Neutron on Matrix. And we hang out there, and, they send me the pictures of the boards they've made, and I make new releases of the firmware and they flash them. And someone else wrote the PC speaker support. So they came and sent me a bunch of patches on GitHub to add support for driving PWM signals into the speaker to make various beeps and boops. So the idea is to sort of foster a community. You can never really build a community, right? You can try, you can set things up, and then either people will be interested in your project and they will turn up. And if they're not, I'll continue to do it by myself because it amuses me. So we gave away some boards and we'll see what happens.
Okay. So what's been the feedback since then? I mean, people just kind of hungry for more features or asking when V2 is coming out?
Yeah, it's an interesting question. So I should probably do more work into finding out what people are doing with their boards. I probably need to chase up all the beta members who aren't hanging out in the Matrix channel on a regular basis and saying, how far did you get? It'd be interesting to know, did some people build the board, they booted it up and they went, cool, I'm done now. I've made a thing and I'm finished. It would be interesting to see how many people didn't manage to get it built. Maybe they built it and it didn't work, and they tossed it in the trash. Yeah, I should do more feedback and find out where we're at. But the core 4 or 5 people hanging out, yeah, we're getting pull requests reviewed, and we've spent a lot of time recently talking about keyboards, which is a subject I didn't know much about, but I've had to learn because I had to write a keyboard driver.
Now, for keyboard drivers, I mean, nowadays usually using USB, but are you just only supporting like PS2 or?
Yep, so old-fashioned PS2 keyboards, which is interesting and retro in itself, right? Because original IBM PC came out in 1981-82. They called it the Model 5150, and it came with an 86-key keyboard. You had a number pad, but you didn't have the little inverted T arrows that we're all used to. That wasn't on the original IBM PC. The arrows were built into the number pad. Page up, page down, home, delete, insert, ends. That little block of 6 wasn't there. It was all in the number pad. And then 1984, the PC-AT comes out, the IBM 5170, and they change the protocol the keyboard speaks, and they add a bunch of extra keys. And now they have 2 problems. One is that when you press a key on a keyboard, it makes a number. Computers work in numbers, and the numbers transferred into the computer. The new keyboard made different numbers for whatever reason. I don't know why they changed it. But the different numbers, they'd go into the software, and the software would be confused because it was expecting some number, X to mean up arrow, and instead it was getting some number Y. So IBM, when they designed the PC-AT, they fixed it. They put a little keyboard controller chip on the motherboard. They translated the codes. So a code comes out of your keyboard, and it gets translated, and a different code ends up in your copy of MS-DOS, and it should be the same as on the original machine. The second problem they had was that they upgraded it to a 101-key keyboard. So what have they added there? 86 to 101, they've added about 15 extra keys on the keyboard, which old MS-DOS software didn't know about. And so they do slightly unusual things where you press one of the new keys, and they actually send you 2 numbers. One of the numbers is broadly similar to a key they had on the old keyboard, and the other number meant this is a new special key. And then the old programs would they would normally ignore the this is a new special key byte, and they would just look at the other one and it would do broadly the right thing. And when you're writing a keyboard today, in 2023, and you want to use a PS2 interface because it's much simpler than USB, you have to go back to what IBM were doing in 1984, 1985, and you have to go and unpick these design decisions. Because otherwise you write a keyboard driver and you press pause, and actually that produces 6 bytes of information. When you press the pause key, it actually emulates pressing a control key, and then I think it's pressing numlock, then releasing numlock, and then releasing the control key. Unless you've been through the history and you understand why that is, a lot of articles on the internet talking about keyboards, they say, yeah, pause generates 6 bytes. Nobody knows why. It's lost to history. I'm like, no, that wasn't good enough. I had to go back and find out exactly why these keyboards are the way they are. I think the IBM PC is just really interesting as a machine and an architecture that was never supposed to be this popular. We were not supposed to be running PCs 40 years later. It was like a one-off machine. IBM weren't that interested in it. It was a skunks work group that built it. It was just supposed to be a cheap thing and not steal sales of their actual computers, their mini computers and workstations. And yeah, through one accident after another, here we are many years later, and we've all still basically got PCs.
So these boards, they actually run a version of IBM?
So the boards I've made, the little keyboard connectors will take a standard IBM compatible keyboard, and I read all of the standard codes that IBM designed that come off the keyboards, and you can still get these keyboards now. The software architecture, because the processor I'm using is actually a Raspberry Pi Pico, I use it because it's $4. I was on Texas Instruments before, and the chip was $10, and the developer kit with the PCB was $25. And when Raspberry Pi turned up and said, here is a 75-cent microcontroller, and you can have it on a board for $4, it's like, well, that's a no-brainer. Why wouldn't I use that as a processor? So because my processor is ARM, because I'm using the Rust programming language, there's not a lot of software I can take from an original IBM PC, even if they're sort of broadly equivalent in power and the amount of memory. So instead what I do is I take inspiration from the design. So splitting the software up into an operating system and a BIOS, where the BIOS is custom for each PCB and the operating system is the same and it runs on top. That goes back to CP/M in the 1970s. That's how MS-DOS worked. Yeah, so go back and I'm a student of history. I love to go back and research these old systems and go, why are they the way they are? Some of these decisions stand up today and make sense to repeat today, and you have to then work out which decisions they made don't stand up today. Maybe there's a better way we could do it. Operating system and BIOS, good decision, I'm keeping that. Writing all of your code in raw assembler, no, that's a decision I've decided, no, we can do better now. I've got a powerful laptop to compile my code on, and I can write nice high-level Rust code, but still get, a compact system.
Interesting, bro. CP/M. I mean, CP/M is a company I think people, unless you weren't in, like you said, that around that time when you were doing all this stuff, you wouldn't know CP/M because they kind of fell out, right? I think the creator of CP/M actually created DOS originally, or am I remembering
Yeah,
wrong?
that's a really interesting story. So CP/M was first. In the mid-70s, the control program for microcomputers.
That's what CP/M stands for.
Yep. I think they had alternative meanings for the letters, but yeah, CP/M ran on the Intel 8080, and it also ran on the compatible Zilog Z80 or Z80, depending on where you're from. And it was the standard. So it was a whole bunch of early home computers would run. If you weren't running that, you probably ran a Microsoft Basic. And then when IBM came up with this idea for a PC, they called up CP/M. They called up Digital Research was the company run by Gary Kildall. And they said, hey, we want CP/M, but we need a 16-bit version because we don't use an 8080. We use an 8086, which is the 16-bit version of that chip. Actually, the 8088, which is a slightly cut-down version, but it's still 16 bits. And there are many, many blogs, articles, stories about exactly what went wrong. But fundamentally, IBM and CP/M, they didn't manage to agree. So they didn't do the deal with Digital Research. They didn't get CP/M for the IBM computer, and IBM had to go somewhere else. And so they went to the people who supplied them BASIC. So Microsoft BASIC was the standard. It's on the Apple II. It's on all the Commodore machines. They were going to do BASIC for the IBM PC. So IBM said, hey, you're doing us BASIC. Can you do me an operating system? And Microsoft said, yes, of course we can do you an operating system. And then they immediately went out and bought one because they didn't have one. So they bought an operating system called QDOS. Apparently stands for Quick and Dirty Operating System. It came from a Seattle company called Seattle Computer Products. It was written by Tim Patterson. And when Tim Patterson wrote QDOS, I mean, he broadly based it on CP/M because CP/M was the standard. And there then was a lawsuit in the 1980s when Digital Research went, hey, MS-DOS, which was the Microsoft version of PC-DOS, which was what IBM called it, which was basically just QDOS, but, fixed up a bit and a new label put on top. It did look an awful lot like CP/M. There was a lawsuit. Some money changed hands. CP/M was eventually available for the IBM PC. It cost more money. So the PC was available with PC-DOS. That was like the lowest price option. And if you wanted CP/M, you had to pay like $250 extra. And it didn't come out on time. It was 6 months late. And so all the software that existed for the PC at the time was all written to run on PC-DOS. And at that point, CP/M was never going to win. They were late, they were behind, they didn't have the compatibility. You couldn't just run your sort of 8-bit CP/M software. You couldn't run the existing PC-DOS software. But yeah, wouldn't the world be a different place if we had Digital Research GEM instead of Windows? There is an alternate universe out there where Digital Research is where Microsoft is today. And it's fascinating how, something that has affected the world so much and had so much of an imprint on the world the release of Microsoft Windows and Microsoft Office and all the tales around Internet Explorer and how that shaped the modern internet. Fundamentally, that all derives from IBM couldn't do a deal with Digital Research to ship CP/M on the PC.
And I think the sad part of the story is Gary ended up ending his life, I think, quite a few years after that, because CP/M went under. I think like you said, there was a couple different lawsuits. It kind of messed up his life and his company.
Yeah, that's my understanding. I think the glory days of Digital Research were behind them as you sort of get into the early 90s. Yeah.
But he was also on another TV show. I binge watch his stuff on YouTube. I think you've seen this one before, right? Where there's two guys talking about kind of like what's the new hotness of the week, and that stuff is 30, 40 years old by now.
Yeah.
Do you remember what I'm talking about?
So I love YouTube because it makes all this stuff available. People take old
Yeah.
video cassette recordings of shows in the 80s. I guess nobody was thinking about archiving this stuff at the time. Broadcast studios can't afford to keep videotapes because videotapes are too expensive. I know the BBC lost a whole bunch of material from the 1970s, like the primary recordings they had of BBC sitcoms that had been broadcast on TV. They just erased the tapes and reused them because who cares, and we need the tapes because these tapes cost a fortune. So why buy more? We can just erase the old ones. So there's a whole sort of subgenre of internet archaeology and sort of restoration of early media. Yeah, the computer show I think we're talking about is the Computer Chronicles.
Yeah, that's the one.
Yeah, Gary Kildare was on there.
He was a host, right?
Yeah, he was on there, and Gary Shafay, was it? Yeah, fascinating stuff. Yeah, retro TV about retro computers. It's a great topic.
But kind of going back to full circle, I mean, maybe we should kind of back up a little bit, right? You're talking about when you were a child, right? You got into this kind of stuff. I mean, was that just, like you said, it was just nostalgia and you're like, okay, I want to bring back some of these old things I used to play with and I want to start from scratch? Because some people, they say, they do these kind of projects because they just want to understand how does it work.
Yeah, I have a background in embedded systems. I did computer systems engineering at the University of Warwick in 2000 to 2004. So I sort of broadly understood how modern systems worked. And then I had this memory of the Commodore 64 my parents bought me when I think that must have been 1989, I think. I can probably pin down the year more accurately if I check, because the Commodore 64 was bundled in a pack, which was an invention of Commodore UK. They realized that just selling the computer was okay, but you'd sell more if you put it in a customs cardboard sleeve and you packed in a bunch of extra software. And so Commodore UK were great at this. On the Amiga, you had the Batman pack with the licensed Ocean game from Batman the movie. You had the Cartoon Classics pack featuring The Simpsons and Dulux Paint. For the Commodore 64, I had the Light Fantastic pack. And that only would have been around for about a year because it's the kind of thing they would have put together with the aim of shifting as many of them over Christmas as possible. So I have fond memories of the Commodore 64 I had when I was a kid, and I had this sort of understanding of modern computers, and I studied Java at university. And then it wasn't till sort of, I think maybe 2015, 2016, I started to think, yeah, wouldn't it be nice to just go back and understand more about the machines I remember from when I was a kid? And the machines I had, the machines that we had at school, the machines I remember friends having, and that's when the sort of the research starts and you start falling down the rabbit hole and trying to understand more.
Well, the interesting part about what computers had before, but they don't do now, which is you'd get a full schematic.
Yeah.
Every single piece, what this piece was and what does it connect to and everything, right?
Yeah, absolutely. And we should bring that back. Like the framework laptop should be how every laptop is. You should be able to understand the technology you're given, because companies would say, oh, but I need to keep it secret so I can make more profits. But what that means is in 5 years' time, when it's broken, somebody has to fix it. Manufacturer's not interested in fixing it. They would much rather sell you a new one. So yeah, that bringing back that sense of here is a computer, it now belongs to you, and therefore you deserve to know how it works and how it's made and what all the pieces are, because you are now responsible for keeping it running. We need to bring that back in all manner of things. I think everything should come with a schematic, and it should come with the firmware and it should come with the source code for the firmware. I have an Android tablet from a supermarket brand in the UK, Tesco. They branched out into Android tablets. It was a good tablet at the time, I think sort of early 2010s. It's useless now. And it's a black box, right? You can't get the schematics for it. I don't imagine I can get any of the driver blobs that have loaded into the Android kernel for the camera and the touchpad, so I probably can't run modern Android on it. And it's sad. It doesn't have to be that way, and I think we can do better.
But obviously nowadays when you have a modern day kind of computer setup, you can buy a motherboard, right? Which is motherboard PCB board is basically synonymous, right?
Yeah.
Okay. So, obviously those things have to be more standardized because now you can build your own PC at home. But back then, I think it was every PCB board was separate for a certain model of computer now.
And again, that's thanks to IBM and the PC. Before you had the IBM PC, everything was custom. The CPM may have been some kind of standard, but the shape your board was in, the connectors it had, the kind of keyboard that plugged in, the kind of TV you could plug in, the kind of disk drives you could buy was not standardized. It was all mix and match. But yeah, it's the standardization of the IBM PC, which many people lamented at the time. I remember in the 1990s, people would rage about the beige boxes that had invaded because they fondly remembered the Amigas of 5 to 10 years earlier and how they were kind of quirky and kind of cool, and nobody felt a beige 90s 486 PC was cool. And sadly, that meant a lot of them got binned. These things had a service life. They ran 5 years and they got thrown away because they had no value to anyone. No one was interested in them. And there's not an awful lot of them left. And now, if you go, actually, I want to put together a 486 machine because I want to run the games I remember and I want to run the software I remember from the early 90s. And I want to run it in that sort of authentic way. I don't just want to emulate it. I want to hear the sound of the hard drive spinning up, and I want to hear the sound of the mechanical clicky keyboard, the smell of the plastics, the whine of the CRT. They make a terrible high-pitched noise. At the time, we were delighted to get rid of them and replace them with flat panels. Flat panels are objectively better in every way, except in reminding you what it was like to be living in 1990.
Well, I heard that people use CRTs for gaming nowadays because they said there's less of a delay.
Yeah, no, the response is instant. And there's certain things like if you wanted to play Duck Hunt on the Nintendo Entertainment System with your light gun zapper, you have to use a CRT because the LCDs just aren't fast enough. They just don't work in the same way. Finding a working CRT is difficult. Keeping it running is even harder because who's making new glass CRT tubes? We forget, but the standard way of watching television, which became the standard way of looking at your computer, was an oddly shaped big glass funnel with a glass panel on the front that was coated in toxic chemicals. And the design of the system was to accelerate electrons towards your face. And they would be mostly, not always, intercepted by this sheet of toxic chemicals, which caused them to glow. And all of the control electronics were swinging this electron beam backwards and forwards 15,000 times a second, which is what made this terrible high-pitched noise. Not a great way to design a display, but actually kind of cool, and I want one.
Yeah, I also remember when we had these CRT monitors for the old beige boxes, as you call them, you would just put your finger up to the screen and you'd get shocked usually.
Yeah, you show that to kids now and they've got, my kids, I've got 2 daughters, they've grown up with iPads and tablets and touchscreens. Sometimes they need to do something on daddy's laptop. So we'll open up daddy's laptop and we'll fire up whatever web page they need to do their maths homework on. And they reach out and drag their greasy fingers across the screen because the idea that there is a picture that you can't interact with by dragging your finger across it is alien to them because they've only known touchscreens. Yeah,
I found that recently. Even with older people too, not even just younger people, even with older people, if you spend most of your time with your phone or your iPad, you switch over to a laptop, but if you haven't touched a laptop in 5 years, you're going to forget because you're so used to that thing.
I think even laptops, are going to become a tool of the past because maybe you would just do it all on an iPad. What is the difference between a bottom spec Apple M1 laptop and a top spec Apple M1 iPad?
Same
one comes with a
right?
keyboard, yeah, but they're broadly the same in many other ways.
Yeah. The only thing is that obviously, like in your developing, you want access to the actual disk, but you don't have that in iPad, right?
Yeah.
But on a consumer, they don't really care. They don't need that.
Yeah, this old idea of I have a storage system and I have files which I store in folders.
And there's a hierarchy.
Yeah, that's just the 1980s way of organizing your computer. And why did they do it like that? Because that was the 1960s way of organizing your office. Your office had file cabinets with drawers that contained folders that contained files. You imagine, you watch the X-Files or some police procedural, they drop the file down and they open it and they look through and there's pictures and words inside the file. That's what we're talking about when we use a computer. That model doesn't make any sense anymore. My kids have never seen a filing cabinet. So why do they need a computer that exposes them to this sort of hierarchical series of folders? I mean, they don't. They just know that they go into the painting app, they click open, and there are all the paintings they've made. Whether they live on the tablet or whether they live on the cloud, it is irrelevant to them. They just know that there's my picture I drew, I can load it, I can send it.
Yeah, I forgot that iPad basically made the file system somewhat more flat, right? Like you said, you have your own separate, like, okay, this folder, which you automatically open up on the Paint app, is the Paint app folder.
Yeah, which is great for security, right? Because why should my painting app I'm using to, color in pictures and whatever, why should that have access to the documents I wrote in the Note app? Why should those two pieces of software have equal access to each other's data? Especially in the modern world when you get your software from the internet. It blows my mind that I download a tool from the internet, especially true on Windows machines. I have to give it administrator rights, at which point I've given it access to my SSH keys and all of the private documents on my computer. They all just get given to my new piece of software. And I have a problem with that because I don't trust software you download from the internet. So the Apple model, which sort of comes from this security mindset, makes a lot of sense because these apps shouldn't have access to each other's data, except in the scenarios where you really want them to. Like maybe I've done in the art app and now I need to load it into a different program because I want to paste it as a frame in a movie or I want to paste it in a document. And now you're like, okay, some of my apps need to access each other's data and some of them don't. And I don't know how to solve that problem. I watch on with interest as people like Apple solve that problem, and I concentrate on writing a very old-fashioned operating system that doesn't really have the concept of directories, where there's no security, there's no login password. You turn the computer on and you have access to everything.
There's no pseudo kind of powers?
On the computer I made, there's not even any user accounts. On the Neutron operating system, it's like MS-DOS. You turn it on, you get the prompt, you have access to everything, which is why I do warn people, do not plug these machines into the internet. It is built for a different time. If you are connected to everything and your system is exposed to everyone else on the planet, you need very good security. You only get away with not having that security when the computer lives on your desk and is never plugged into anything else, and you've got a good lock on the door.
Now, I want to skip forward back to kind of where we are today. Well, a little bit more forward with the Rust working group for embedded systems, right? So where was the idea to start that up?
So that came in, I think, 2017. And there are a bunch of people doing some Rust on embedded systems, myself included, James and another Jonathan and Jorge and a bunch of people, all doing great work individually. And somehow we managed to find each other and come together and, well, we need to make Rust on embedded systems work better. Back then in 2017, you couldn't make a Rust program run on a microcontroller using stable Rust. You had to use nightly Rust because you needed unstable features. I remember, it's my new program I'm running on a microcontroller, I've needed 7 unstable feature flags in order to make this work. And that's just not good. We agreed, stable Rust is just a better foundation for building software. And that was one of the early goals of the Rust Embedded Working Group, was making embedded work with stable Rust. And we were able to talk to the core team and the libraries team, as it was then, and we got the changes made so that we could run Rust on a microcontroller using the stable compiler. And a bunch of those changes went in the Rust 2018 edition. And since then, the group has grown and grown. And it has a sort of a bunch of related groups to do with each kind of processor family. Because microprocessor manufacturers, microcontroller manufacturers specifically, are very keen on selling you their chips. And they give you their software stack for free. But the software stack is only good when you're using their chips. And if you want to use somebody else's chips, you have to use somebody else's software stack, and these things are not compatible. And they make it deliberately or otherwise, you'd have to ask them. But they certainly make it difficult to move from one manufacturer to the other. So the Rust Embedded Working Group said, no, we want to build a world where all microcontrollers are equal and you can move from one to the other. Because if somebody's writing a driver for an Adafruit LCD screen or a Bosch carbon monoxide sensor or a GPS receiver, when we have a package manager and we are used to the idea of sharing our software and downloading our dependencies, why should I have to write those drivers multiple times, once for this microcontroller, once for that microcontroller, once for the other? They should be able to do it once on platform A, and then someone else should be able to turn up using platform B and be able to reuse that good work. And so the Rust Embedded Working Group set about defining a hardware abstraction layer. They described the fundamental operating units of the microcontroller at an abstract level so that you could write your Bosch gas sensor driver against a generic interface that describes an I2C peripheral. Precisely what I2C does doesn't particularly matter. We just know that you have the ability to read some bytes and you have the ability to write some bytes. So we can describe that in a trait. And if the driver is written against that trait, which lives in the Rust embedded HAL, the trait is implemented for 6, 7, 8, 12 different kinds of microcontroller from different manufacturers. So now I can reuse it. I can move it from platform A to platform B, and that's really powerful. We had mechanisms to do that in the past, and they weren't popular because it involved a C structure full of function pointers, and that cost you performance. And it was much better if you just called the I2C driver directly. With Rust, we get zero cost abstractions. We get to describe our I2C peripheral in generic terms. But the machine code we get that runs on our processor is as good as if we'd handcrafted it. The traits go away, the system monomorphizes and says, oh, you are using some T where T is an I2C device. In your case, T is I2C driver for some chip family. So I will just assemble it all together and give you high quality machine code, even though you are writing nice portable software. And that's the great gift for Rust on embedded systems, is it lets you have portable code and high performance code at the same time.
And also in some nice, how do you say that? This higher order function kind of style where you can do functional programming.
Yeah.
Things like that.
Even on a microcontroller where you don't have the standard library, you still have iterators, you still have closures, you still have modules and unit tests. And at Ferris Systems, a really nice logging framework so you can have nice verbose messages that explain what your system is doing. But the way it works is the strings, the text messages that get printed don't live on your microcontroller. Your microcontroller simply says, I am printing log message 67 and the argument is 4. That goes down the logging mechanism into your computer, and your computer gets the note that says the microcontroller has printed log message 67 with the argument 4. And it's your laptop that then looks in the binary that you compiled and goes, log message 67, oh, that is the temperature is currently, so I will print the words on screen. Sending the message 67 is much shorter than sending the temperature is currently. You can see how that's a much more efficient system. And it's because we have a build.rs file, and it's because we have macros and procedural macros that we're able to build these kind of really powerful tools that just let us write better, more efficient, faster, safer code for our microcontrollers and have a better time doing it. Maybe build these things in C, but I think they end up more brittle. They end up more difficult to maintain, and they end up less portable.
Now, I did want to ask a question about the word microcontroller, right? Is that exactly the same meaning as a CPU? Because I always hear that, but not really sure
So
if
a
that's the truth.
microcontroller is somewhat distinct. So we have a generic idea of a processor, which is the same as a central processing unit. This is a piece of silicon which knows how to read instructions from memory and execute them. And then in executing them, it will read and write data from memory. In ye olden days, when you bought your Zilog Z80, you bought your Intel 8080, your MOS 6502, these were central processing units. They didn't have any memory. They didn't have any input output. They only had data pins and address pins. And they would set the address pins to say, I am accessing address 1234, and I'm writing these 8 bits, or I'm reading those 8 bits. And you would need to build them into a system by adding memory and adding some kind of I/O chip. And it was the differences in I/O chips and video interface chips that really make the difference between an Apple II and a Commodore 64. And the Amiga was famous for having special custom chips. Now, when we get to the sort of the age of integration, the late 90s, when people start making portable devices, mobile phones, it doesn't make sense to have 4 or 5 different chips on your circuit board. Why don't you just combine them all together? So now you have a single piece of silicon that contains the processor, the CPU, as one corner of the piece of silicon. And then it has the I/O interfaces, the memory controllers. So when you get to the sort of the age of integration in the 90s, when you're trying to build a mobile phone, early mobile phone, you think, well, what doesn't make sense to have all of these separate chips on the circuit board? Why don't we just design one piece of silicon that has a processor in the corner, and it has the memory controller, and it has the I/O controller, and it has the display controller, and we'll just put it all on what they call a system on a chip.
SoC.
Yeah. So you've taken the entire PC motherboard and you've shrunk it down to a single piece of silicon.
That's not entirely true, right? Because you have to have some pieces that are not there. Obviously, I don't know what access to the hard drive or something. I'm not too sure, but there's other pieces on a board besides just those pieces.
Well, so it depends. If you have a Raspberry Pi, I mean, there's basically nothing else. The system on a chip, and it has the memory chip, and I think the Ethernet is separate. So the Ethernet sits on a little USB bus. But a Raspberry Pi has very few chips on it. A modern PC motherboard, they have taken longer to move to the system on chip approach because it gives the mainboard manufacturers flexibility when they can chop and change the memory controller. Memory controllers used to be separate. You bought a Pentium 2, a Pentium 3. Your memory controller came from Intel and it lived in what was called the chipset. It's called the chipset because on the original IBM PC mainboards, that was probably 40 different 7.4 series logic chips. It got compressed down to 2 or 3, but the processor was separate. AMD said, no, let's put the memory controller on the chip. When the AMD Optron came out, the SD-RAM was wired straight to the processor. There's no memory controller. Later, you find chips with integrated video. So Intel include graphics, AMD include graphics on their processors. Really, there's not a lot left. There's PCI Express and hard drive interfaces. And actually, you can get modern processors today where even that is all integrated. The benefits of integration are it's cheaper to make one chip than it is to make 5. Your circuit boards can be smaller because you put fewer things on them. The downsides are you've lost flexibility because you aren't able to sort of mix and match bits and pieces. So a microcontroller very specifically is a kind of system on chip, but it's generally around the processor it uses and the memory interface. So modern computers use this Unix approach of virtual memory and physical memory, and that means you need a memory management unit. Modern systems, the distinction we generally have is a microcontroller does not have a memory management unit. So it is a system on chip with no MMU. There is no virtual memory. There's no page file. There is memory, and that's as much as you've got. Every modern operating system requires a memory management unit. And so that puts them above the world of microcontrollers and in the world of applications processors. An amusing note, if nobody's spotted, ARM, the company from Cambridge, designs a family of processors. They call them the applications processor, the Cortex-A line. They have the microcontrollers, the Cortex-M line, and they identify a sort of a region in the middle, which is hard real-time system. So this is you're in charge of the brakes on your car, or you're in charge of the motor inside the hard drive. and they call that the real-time system. And that does mean that ARM's product family is the A, the R, the M, and the product family itself spells ARM.
Well, I thought ARM actually stands for, because they were making computers only for UK. Right?
Yeah, so they were a spin out of Acorn. So
Acorn,
ARM originally stood for Acorn RISC Machines, because it was a RISC processor. And that then got renamed when Apple invested in the early 90s, Apple and VLSI. That became Advanced RISC Machines. ARM also have a document called the Architecture Reference Manual, which means there is a document known as the ARM. It's just something about Brits and puns. This is what we love about the Rust community, is it's all the puns on oxidization and ferrous and on all these kinds of things. Brits love a good pun.
Yeah, the ARM thing is interesting. So you talked about the word RISC, right? I know what you mean by RISC. RISC means reduced instruction set, right?
Mm-hmm.
But everybody at home knows that one. So maybe you can talk very briefly about RISC versus, I think probably the biggest comparison you always have is Intel. Intel versus...
Yeah, so you had to remember that processors didn't always used to be chips. Processors used to be a box of circuit boards the size of a big suitcase. And it was only later that they worked out they could shrink them down to a single piece of silicon, the silicon chip. Those machines generally had pretty complex instructions. You had an instruction for go through a piece of memory and find me the first byte that is 0. They just kept adding these wildly complicated instructions, which made the software developer's life a bit easier because there's probably an instruction that does just what you want to do, which is great if you're writing assembly. But it makes the chips complicated. And when the chip pulls in the instruction from memory, it's got to look at it and go, gosh, what have we got here? Okay, well, the first 17 bits are this, so that probably means we're doing that kind of operation, and then these bits are that. So there's a bunch of decoding work. It's great to be in the talk we had earlier today at Rust Nation on binary translation, where they looked at RISC-V. RISC-V is the latest in a series of RISC designs. ARM weren't the first. They got the idea from work that was being done at, I think, the University of Berkeley. I think RISC-V is called RISC-V because it's the 5th generation of RISC architecture from Berkeley. The idea is make the instructions simpler. RISC-V only has 39 instructions. The original ARM only has about that number. So the computer, the processor, can only do simple things, and you have to write more complicated software to get the outcome you want. The trade-off is you have to write more software. You need more instructions, but the processor can be much simpler because it doesn't have to decode as much. It's a much smaller set of things it's doing. And the only reason that CISC kind of stuck around for so long was because that's what IBM put in the PC. So the reason that CISC processors hung around for so long is simply because that's what IBM put in the PC. They used an Intel chip. It had complicated instructions. We like our compatibility, so every generation of Intel chip is like the previous one, but with extra instructions bolted on. Your modern Core i9 13th generation Rocket Lake machine is fundamentally an 8086 when it turns on, and it has to go through a bunch of steps to get it into progressively more modern modes so you can run your operating system. The ARM and I think RISC-V in the future have just cleaned up in every other area of computing. Where the backwards compatibility is not a problem, the RISC processors use less power because they are smaller and they are simpler. Famously, the first ARM chips that Acorn got back, they forgot to plug the power supply in, and the tests worked, and they were powering themselves.
It's a low-powered chip, right?
Yeah. They made it low power because they couldn't afford to put it in a ceramic package. And so they wanted to make it work in a plastic package. So they designed it to be low power, to be cheap. The power supply wasn't connected, so it was powering itself from the I/O signals coming from the other processor. It was powered through its data and address lines, and it still worked. And they were like, gosh, okay, yeah, maybe this RISC thing has something in it. Obviously, in the mid-90s, it didn't go so well. Their desktop line fell apart. Acorn itself folded or got absorbed into other things. But ARM, by putting chips in the Apple Newton, and then later designing chips for the iPod, and then the iPhone, and then, the iPad.
Not even just that, basically all modern day chips are kind of based off of ARM, right? ARM design. For mobile devices and smaller.
Yeah, for mobile devices, ARM, wall-to-wall. Microcontrollers, yeah, pretty much. You get into esoteric stuff in vehicles, you still get a lot of PowerPC. If anybody remembers late 90s Macintosh, they jumped to the IBM PowerPC standard before then going to Intel. There's still other architectures around. Design seem to have hoovered up much of it, and it's PCs that cling on with Intel, and they are sort of the last holdout of CISC, which is wild because the core itself is really a RISC core. It's just got this front end on it that understands how to decode all of these complex instructions, which is only really there for backwards compatibility. Intel did try to make this go away. They tried to release a processor called the Itanium. Now, many journalists refer to it as the Itanic because it sank. They had this idea of making a new processor with a new set of instructions, and we need new compilers, and it's better. And nobody bought it because it didn't run the software they already had. And that's fundamentally what people want.
Actually, there's one question I have about this that always confuses me, right? You'd figure that if it's a RISC, so RISC instructions is, like we said, reduced instruction set. There's much less instructions. So to me, if you're doing more things just to get one operation done, that sounds like it should consume more power and be more inefficient. But somehow it's the opposite.
Yeah, because when you design a processor and it's made of these transistors, the transistors, there's different ways they can consume energy. So they consume energy just when they're doing nothing at all, called leakage current. And then they consume energy when they switch. And whether you design a sort of a big complex processor or a simple processor that has to do more, these things can trade off against each other. So if your processor is smaller and contains fewer transistors, it has less leakage current. And maybe the individual steps of the program can be executed faster because they are simpler. So you can turn the clock rate up, which means you can get the work done and then put the chip into its low power state. So yeah, it seems odd that writing longer software ends up saving you power, but because of the way chips are designed, that's how it works out.
But I think the other issue too is that they keep adding more and more instructions, but these instructions become very specialized to where it's like, well, maybe even people's consumer chips nowadays, they're not even actually using most or even a quarter of them.
Yeah, I think there's large parts of your processor that you don't use on a regular basis. And you could probably even make an argument that ARMs aren't that RISC anymore because keep adding more instructions. I specialize in the microcontroller space. The Cortex M0, I've seen a great diagram of all the instructions. And the Cortex M0 is sort of like this small square, and they've drawn all the instructions in it. And they said, okay, the Cortex M3 that came after, we added these, I don't remember the number, like maybe 50 extra ones. And the Cortex M4 and the M7, well, here's another 75 instructions we've added. So you can do accelerated multiplications by a certain type of number and these sort of extra features, which, yeah, most software doesn't touch. But if you're doing high performance CAD or, if your application needs that instruction, you'll be really grateful it exists. And I guess these are always in tension. How complicated do you make the chip to get the performance that people need versus the price people are going to have to pay for it?
I think we kind of drift off the main topic, which was kind of talking about, the Rust working group, the embedded working group. So you when you started to get some of these features put into stable Rust, was that when you guys were already officially a working group of Rust, or was it before?
Oh, good question. Yeah, there is sort of some timeline, some spectrum from scrappy group of independent people who like doing Rust and would like it to work better on microcontrollers to at some point we became an official working group, one of many other working groups. And I couldn't put my finger on precisely when that happened, but I don't remember there being like a day where I woke up and there was an email that said, ta-da, you are now an official working group. It was just a gradual thing over time. We did the weekly meetings, we did pull requests, we discussed things, we used the software. I mean, that's the key thing. We actually tried to build things with the software we were writing. And then at some point we're like, oh, yeah, hey, people in sort of the Rust core team are aware of the needs of embedded developers. And that is a road we're still on. And I think there's still more we can do. The Embassy asynchronous embedded framework, it does great work, but I believe it still needs some nightly features to get the most out of it. And so that, there's still more we can stabilize. And I guess software is like RISC versus CISC processors. how many keywords do you add to the Rust language before you say, that's enough? I don't know where that limit is.
Yeah.
Probably haven't reached it yet. Will we know when we've reached it? I don't know. Will we accidentally continue down this road and keep pouring keywords and extra features into the language and then go, oh no, we've made a bit of a mess. Maybe we need to invent a new language with fewer keywords that's easier to understand.
I believe what they do now is just make a new edition, right?
Yeah, you make new additions, but at what point do you say we've done enough and this language is okay and it doesn't need tweaking anymore? Like C, they changed bits of C. They haven't changed it much. It's broadly been very similar. Certainly the C people write as opposed to what the standard says you can write hasn't changed much in the last 20 years. It'd be interesting to watch Rust as it sort of heads into that mature space where we're like, yeah, this language is broadly done and the interesting bits happen in the third-party ecosystem. But we're not there yet.
Now, using Rust for this embedded work, I mean, is it a lot of challenge to bring in new processors, new systems?
No, because that's something we've had to do. We started from scratch and various people have gone, here's a processor. I sat down with the Raspberry Pi RP2040. It was early 2020. I think we were in lockdown. I was the mayor of St. Ives at the time and I was looking to do some fundraising events. I couldn't do any because the pandemic was on. And so I sat down with this chip and went, okay, I'm going to do a live stream. I am going to live stream me unboxing my brand new Raspberry Pi Pico. I've not read the datasheet. I've read the cliff notes and the website, but that's it. And I am going to make Rust run on this chip. And we are going to get blinking LED before we're done. And we did. The live stream was about 6 hours. I think I stopped for lunch in the middle. I was hungry. And we got Rust running on a brand new chip. And the way you do that is twofold. You can either start with some C code, translate it line by line, or you can start from the manufacturer provided definitions of the chip. Manufacturers will generally provide you an XML format file that says, your memory is here, you have a UART peripheral called UART0, and it has 6 registers, and the first register is split into 4 fields, and the third field means this. The huge files, loads of detail. If that file is accurate, we can feed that into a program called svd2 Rust, the digit 2, and it makes a Rust file that describes the chip. And once I've got that, I can easily turn on peripherals, access the GPIO, and from there you build implementations of the HAL traits we talked about, and then you're off to the races, because then you can plug in all this big, rich ecosystem of third-party code which sits on top of the interfaces you've built. So yeah, we've worked on the process of building Rust up from scratch on brand new microcontrollers simply because we've had to do it so many times.
Now, doing the no standard, right, for Rust, I mean, there's still quite a bit of the library which is still available, right?
A surprising amount, yeah. So you can have closures on a no standard system. You can have option and result. You can have enums with associated data. You can opt in to the allocation library, which will get you big string with a capital S, hash maps, vectors. But again, there's some unstable features required to use those. So if you want to stick to stable Rust on no standard, it's just libcore. You can build a lot. I've built an entire computer with a disk drive and a file system and keyboard and video, and the entire lot is done in core, only using libcore, no lib standard, no memory allocation. Yeah, you can do a lot.
Now, do you find it quite painful to have to do this kind of work or no? Because you are missing some somewhat key features, right?
Sometimes it's nice to say, I would just like a string. I don't know how big this string is going to be until I've formatted all of my arguments. And it's kind of annoying to have to guess in advance. We have some great software to help with that. My colleague Hocher wrote a library called Heapless, and that gives you things like vec and like string, but they exist using a predetermined amount of memory. So they can't grow. Their memory allocation is pre-supplied. But once you've done that and you said, okay, my string is never going to be more than 64 bytes. Check, that's plenty. Once you've done that, the heapless string looks a lot like a regular string. And so at that point, you can kind of forget you don't have lib standard anymore. And you can still have nice things. You can still do write line. You can still do formatting. As I said, you've got closures and enums and option and result and all that good stuff. So it's not too bad.
Now, after working with C for some time, working with Rust for some time, is there times that you think Rust would be less suitable than C for something?
I don't think I've ever.
Because I know there's some features in C that are not available in Rust that some people wish they had, but I forgot which ones they were off the top of my head. But I'm just curious about you.
Unless the rest of your world is in C, I can see that there is a cognitive load to switching languages. So if you are doing 90% C and you need to write the other 10%, you do have to ask yourself if the cognitive load of switching languages to and fro is worth it. And it may be for the advantages Rust gives you. But generally, Rust has raw pointers. We can access raw memory. We can design structures that look like objects, like peripherals in our memory mapped I/O. So yeah, no, I don't think there are many cases where I'd start a project and go, I'm going to use C. There have been a couple of projects where I've started and I've gone, I'm going to write this in Python, but that's simply because I was only writing 10 lines and I knew what I needed to do and it was easier. So I do still sometimes reach for scripting languages. But even then, I sometimes try out the advent of code. I haven't managed to finish it in recent years. I do the first dozen or so. I like to do those in Rust because built up a little library of tools which will take in my game input, split it up into lines and split the line into integers, and got all that available, then actually plugging the logic of the puzzles together is fairly straightforward. But yeah, not many scenarios where I'd go back to C these days.
Okay. I think we spent quite a bit of time together. We talked a little bit about the working group, but not a whole lot. I mean, is there something else that you think we should know before we sign off?
You should know that we are available online and you should come and talk to us. If you have any interest in Rust on microcontrollers, come and find the Rust embedded chat rooms on Matrix. Search for Rust embedded and you'll find the pages on rustlang.org. You'll see the book we wrote. The Discovery book is your introduction to embedded systems using Rust. You'll find the Rust embedded book, which is you already know embedded systems, so here are all the Rust specific bits. And you will find our dark and arcane knowledge collected into a book we call the Embedonomicon, which is all of the scary bits of unsafe you need to do at the very lowest levels to make Rust work. So there's 3 really interesting books. Check out the awesome embedded Rust page. There's just hundreds of links on there, fascinating projects. Sure, you can find something that will grab your interest, and there's another rabbit hole you can dive down. So there's loads of great resources, and I encourage everyone to check them out.
Thank you for your time, and it's good to meet you and to hear more about the Rust Embedded Working Group.
It's been a pleasure. Thank you very much.